Okay, so 5.2, impedance with two-port elements. So in the last lecture, we only considered the impedance of a single element that is one port, or combinations of one-port elements. So we want to also consider two-port elements because that's where the transducers come in, right? That's how we go from electrical to mechanical, or we go from fluid to mechanical, or we go from fluid to mechanical, or thermal to mechanical. We're mechanical engineers here. Did I mention that? Okay. So the two types of energy transducing elements, transformers and gyrators, reflect or transmit impedance through themselves, such that they are felt on the other side. So the impedances on one side can be felt on the other side, right? So if you had a motor, for instance, and you think of the impedance of the maybe the inertia and the bearing on the mechanical side, and you try to drive the electronic side, the impedance of the mechanical side is felt on the electronic side. Similarly, on the electronic side, so if you were to go up to the road or the say a moment of inertia on the mechanical side and try to spin it, you're going to feel the electrical impedance as well. So you can feel the impedance through this transducer, and we want to derive expressions for how that happens. So how do you find out how much impedance you're going to feel through that interface? So that's what we'll derive here. We'll derive it thoroughly for the transformer. So for a transformer, the elemental equations are that the cross variable on side 2 is equal to the cross variable on side 1 divided by the transformer ratio, TF, which is just a constant, right? So it could be like the motor constant, for instance. And then the through variable on side 2 is equal to negative TF times the through variable on side 1. So that could be like the force or the torque and the current for a motor. So the Laplace transforms of which are just the same expressions except for they're of S. Because there's no derivative, we don't have any explicit S's pop up. If on the 2 side, the input impedance is Z3, as in figure 5.2, right here is the figure. We're looking at this transducer where you got a side 1, say like the electronic side, and then side 2, say the mechanical side. And on the mechanical side, say, side 2, you've got some impedance, Z3. So maybe like this was a whole network of stuff over here, and you combined all those impedances to make Z3, for instance. Or it could just be a single element, but you could have a whole thing happening over there. What we want to see is, how is Z3 felt over on side 1? Okay? How does it go through this? So the equations of 511, in this case, are subject to the continuity and compatibility equations that V2 is equal to V3. So the across variable of V2 is equal to the across variable of V3. And F2 is equal to negative F3. If you looked at a contour around this node, for instance, and you would see that the through variable through 2 has to be equal to negative through variable through 3. Substituting these into equation 511 and solving for V1 and F1, we have these expressions. So we eliminated the 2 terms. So V1 is equal to TF V3, and F1 is equal to F3 divided by TF. So that's a start. What we really want to know is, remember that the impedance, the input impedance for the system is going to be the relationship between V1 and F1, right? So we're trying to relate V1 to F1, and so we gotta somehow turn a V3 or an F3 into a V3 or an F3 so that we can eliminate those variables. We've got 2 equations, we gotta eliminate those 2. So the elemental equation for element 3 is that V3 is equal to FZ3. Now this is true if you take, so when I say the elemental equation, I'm meaning the Laplace transform of the elemental equation, right? So usually when we say the elemental equation in the past, we've always meant the time domain one with the time derivatives associated with it. But now I'm saying, okay, if this is a Laplace domain situation, which when we're talking about impedances, it's what we care about, then this is the elemental equation. In fact, this is the elemental equation for every element now in the Laplace domain, right? Because you can always relate the through and across variables of any element with its impedance, right? So I'm saying that's true. It doesn't matter what the element is, what element Z3 is, any impedance is going to have that elemental relationship. So this can be substituted into the through variable equation, for instance, to yield that F1 is equal to 1 over Z3 times TF times V3. And now I'm poised to work our way back from V3 to V1 by applying the compatibility equation. That so you can do this, or you can just use this equation. However you want to eliminate it, you got to get between F1 and V1, and you get F1 equals 1 over Z3 TF times V2, which is equal to 1 over Z3 times TF squared times V1. So I did 2 steps there. I really only needed to do 1. But however you eliminate them, now I have a relationship between F1 and V1, right? That's what I wanted. So solving for the effective input impedance, Z1, we know that Z1 is, by definition, V1 over F1, right? So I can solve this for V1 over F1, and I could essentially just move this over to there and F1 over to there, and I get that Z1 is TF squared times Z3. So TF squared times Z3 means that in order for us to reflect the impedance Z3 through this transducer, we have to multiply it by TF squared. Okay? And that's how it's felt. So it's felt, the impedance on one side is felt by as felt as an impedance that is on the other side multiplied by a factor TF squared. So that is for the transformer, okay? For the gyrator, with gyrator modulus GY in the configuration shown in 5.3, so same thing but a gyrator, meaning that the elemental equations state that V1 is related to F2 and F1 is related to V2. Via the gyrator modulus GY. It's another constant, right? So in this configuration, a similar derivation yields the effective input impedance, Z1, to be the gyrator ratio squared divided by Z3. So it's similar, but there's an inverse in there. So that is those are our 2 derivations. So we've got now an understanding of how an impedance from one side is reflected through. It's commonly called reflected through. I don't really know why it's called reflected, but it is. Okay, so here's an example. Draw a linear graph of the fluid system. What is the input impedance for an input force to the piston? So it's also, there's a little bit of mechanical happening here too, right? There's mechanical piston cylinder arrangement. Then we've got a fluid system. So let's draw the linear graph first. So we've got a mechanical side. There's not a lot that happens on the mechanical side, but we do have it. And then we've got a fluid side as well, right? Maybe I'll put this over closer. So we've got a ground here. So this is the mechanical ground, which is to say like v equals 0 would be a reference velocity. And for the fluid system, we might say the ground is P atmosphere, the pressure of the atmosphere. So all of our pressures then will be gauge pressures, right? Gauge pressure. You guys are in fluids right now, right? Am I using that term correctly? You guys are the experts. I haven't taken fluids in like a decade or more. More. Okay, so we've got ourselves a mechanical side that's pretty much just a force source, right? We have a force source that comes in, and it immediately goes through this transducer. This transducer takes a force and it gives us what? What's on the other side of this pressure? We would say that, for instance, Fs is going to equal some pressure. We could just call this like P naught or something like that. Times the area, right? That would be the relationship there. So this is a through variable, the force, right? The pressure is an across variable. So what do we have here? So this is a, well, yeah, I mean, you can think of it as a transfer function, but this is a, thinking of characterizing the transducer, this is a gyrator, right? Because we've been so used to seeing transformers. Transformers relate across to across, through to through. Here's one that relates a through variable to an across variable. Wild, right? Whew. So we've got ourselves a gyrator. And on the, so it interacts with the fluid side. So we can draw this like crossing thing here, gyrator. And it's so we have a gyrator modulus GY. And on the other side, we've got, what do we have? Resistor R1. And it goes into a fluid capacitor. So I didn't say anything about a height difference here. There could be some height difference, but I didn't. I drew this as being like really wide, and it's clearly not to scale. So I didn't say anything about a height difference. We don't have to worry about a pressure drop there, any pressure head. But we need to be careful about that, right? But R1, and then it goes into a capacitor, right? C, which the capacitor exposes it to atmospheric pressure at the top of the tank, right? So it's got to reference the atmospheric pressure. And then it's going to go through R2 and I. As I say, this is a long pipe, so it's got to have an inertance and a resistance. And we want to go through both of them, R2, the same flow rate through both of them. So they should be in series, and I. And that also goes out to atmospheric pressure here, so should go to ground. So there's our linear graph. And we want to know what the equivalent impedance is, the input impedance of the whole system is for this force source. So we have to find the equivalent impedance of all of this stuff over here and then reflect it through the gyrator, right? So,
If I may ask a quick question.
yeah, sure.
So if we were to typing it out, it makes sense to me, but I'm just trying to see where would the gyrator be located on the actual diagram itself? Would that just be where the piston interacts with the pipe?
Exactly. So yeah, it's right here. So it's where we go from a force to a pressure. Yeah, it's right here in that interaction. Yeah.
In this case, we're neglecting the mass of the piston.
We are neglecting the mass of the piston. So we could say, well, there's some mass of this piston right here, right? So we could do that. I'm going to ignore that though for this example.
So we're doing a classic physics problem where we have massless piston.
Massless piston. I mean, there's no reason we need to. It's just that in my notes I ignored it, so I don't want to do. I want to make sure I have the right answer. So, but we could. I mean, it would be just another step, right? We would have to take whatever comes out of the gyrator in terms of impedance and combine it in parallel with the impedance of the mass. So there's nothing that's like stopping us from doing that. It's not that we can't do it. It's just that I didn't do it. So it's a foam piston. It's made of foam, super light. Okay. So we've got. Never make a piston out of foam. Just don't do it. Okay, so we got to find the input impedance. And once again, because we have 1 minute left, we'll do a one-liner. Not hard, though, once again, because we've got all of this stuff, which we can combine using the same sort of method. So we'll do ZR1 plus, because it's in series with, these two are in parallel, and then these two are in series. Oh my goodness, we're gonna do this all at once? We are. We're gonna go with ZC times the series combination of R2, so ZR2 plus ZI, right? Divided by ZC plus ZR2 plus ZI. We could put parentheses here, but they're superfluous. So that is the impedance of over here, which is like our Z3 from the above derivation. So what we need to do is divide GY squared by that, and that will give us our Z that we're looking for, our equivalent impedance. Because we have the G, when it reflects through, remember from this expression here from 516, the impedance Z3 is going to be felt on the Z1 side by GY squared divided by Z3. And that's it. Okay. That was fun. Had a good time. All right. See you guys Friday.